Okay, so we're going to do a quick lesson on nuclear fission. So please put your date up here. So in this lesson, we're just going to look at what the two isotopes that are used to power nuclear reactors. We're going to understand the process that powers nuclear fission and describe exactly what a chain reaction is and what happened to the parent nucleus during nuclear fission. So if you want to start this off, please have a go, refer back, see if you can solve this. So here, and look back in your notes and see if you can see what an isotope is. So have a go at those two right now. Take a pause if you need to, and I'm going to start going through it in 10 seconds. Okay, the isotopes. So these are two isotopes, 235 and 238. So I'm not actually going to write it in here, but what is an isotope? It is a atom or a nucleus with the same number of protons but a different number of neutrons. And these are isotopes because they both have 92 protons, which is here. And if you want to calculate how many neutrons, then you need to take the top number, which is the mass number, and subtract the 92 from that. So the first one is going to be 235 minus 92, which is 143. And this is going to be 238 minus 92, which is 146. So they are both chemically identical, but they are different isotopes. Now, if I was in my lesson now, I'd probably have a little chat about nuclear power and what we know about it already. But I am just going to move on now and explain a little bit about what this is and how nuclear power stations work. I suppose the key thing to understanding the nuclear fission is really you already need to understand this process. Now this process is a sheet we've already done in your booklet, and I got you to use all these words to describe. So you might just want to pause the video here and look at what you wrote down in this section here. Because fundamentally what's going on here, this is general nuclear decay. So this is a not particular nuclear fission, and we've already covered this earlier on in this topic. And we have a parent nuclei. The parent nuclei decays. Yeah, so there's decay into a daughter nuclei. And when it decays, it emits out these things, perhaps, or a mixture of them, alpha, beta, and gamma radiation. Alpha, beta, gamma radiation. Well, it'd be like a nucleus, and this was an unstable nucleus. We had that, and really, I was going down a slightly different avenue when we did this in the other topics. So we just really talked about activity, count rate, and Geiger Muller tubes. But fundamentally, this is what's going on here. We're having an unstable nucleus, and it decays into something else, giving it alpha, beta, and gamma, and energy. And fundamentally, that is what nuclear decay is. Nuclear fission is a specific type of nuclear decay. So if I go to this nuclear fission diagram, you can see it looks very similar. We have a parent nuclei here. Now, the interesting thing about nuclear fission is this particular parent nuclei is uranium-235. This is the one we're going to focus on. There is another one called plutonium, but more commonly that has to look at uranium. And this is uranium-235. Remember, go back, uranium-235, it's got 92 protons, 100, and it's actually reasonably stable, uranium-235. However, by the addition of one neutron, we'll end up with uranium-236. Uranium-236, made in this fashion, is extremely unstable, and it undergoes nuclear decay. And the type of nuclear decay it goes under is called nuclear fission. In nuclear fission, the key idea is that you normally get two reasonably large daughter nuclei. As well as the daughter nuclei, instead of getting alpha, beta, and gamma, what you normally get coming out of a nuclear fission reaction, or particularly in this one, is more neutrons. Now, if you remember, what made the uranium-235 unstable was a neutron. And in this reaction, what's actually happening is you're splitting this nuclei in half. You're creating two daughter nuclei. You're getting quite a lot of energy because we're losing some mass during this process, and that mass gets turned into energy using Einstein's formula E equals mc squared, and then we get more neutrons. Now, the interesting point about this is it was the neutrons that made the uranium-235 unstable in the first place. So if we look back at this chart here, we can see we start off with uranium-235, and it has a neutron added to it, and it splits apart and it creates two daughter nuclei. In this case it's barium and krypton, but it also produces, can you see, 3 more neutrons. Now those neutrons are all capable of going and smashing in to another uranium, and this is the second stage of the process here, because if you take one uranium, split it apart and get 3 more neutrons, then you're capable of maybe splitting apart 1, 2, 3 more uraniums. Those uraniums then move off and they break up some more krypton, barium, create daughter nuclei, but each one of these also then produces 3 more neutrons. And each one of those neutrons is capable of going on to keep the equation going. So you can see, particularly in this one, this neutron's missed because there's nothing there to go into, but it's still being created. And this is why nuclear fission is so very good at creating energy, because it creates what we call a chain reaction. Because the initial conditions for creating it were just added by adding 1 neutron. You might want to go and look. There's a nice little FET applet. You know, one of my favorite is FET. If you go to FET, you can actually look and have a little play with this and add uranium-235s. And all you need to do is trigger off 1 uranium-235, and you can set the whole bunch off. It's just type in FET nuclear fission, and you can go and see and have a little play with that. So I would say the key idea here, I mean, there is quite a lot of videos on YouTube about this. I would suggest this one is quite good. It's aimed at GCSE physics. I think if you want to have any more explanation, if you want to go and either review my explanation of what's going on here, or you can go and have a look at this video. I think that the last thing I want to do before I finish on this, though, is that we're going to go through this in a minute. I think if you're trying to do a GCSE, you're going to want to answer be able to answer a good description of what's going on in this diagram using all these keywords. This is what I would do in lesson now. So I want you to, if you've got your workbooks, go to this page here on nuclear fission. I want you to give a nice, full example explanation of what's going on here using all of these keywords as fully as possible. Once you've completed that, I'll just you can carry on playing the video. So pause the video now, and once you've completed that, you can come back and I'll just show you my model answer. Okay, so I'm going to show you my model answer now to what I would write for here. So fundamentally, I'm going to give this, I've written out a pretty full, extensive answer here. Obviously, other answers are available. This is just my particular version of the solution. Larger nuclei, particularly uranium nuclei, are made unstable by making them absorb an extra neutron, making an isotope. The large nucleus decays and breaks apart, releasing energy. More neutrons and more neutrons and the daughter nuclei. This is fission. Amongst the smaller fragments remaining are more neutrons, at least 2 or 3. These neutrons are absorbed by more of the uranium nuclei, which in turn decays, releasing energy and causing a chain reaction. Now, clearly, I'm not exactly answering a particular question here. This is just a description of the process here. I think, hopefully you can read that and have a good understanding. If you can get close to 11, if you've made all those keywords appropriately, then you've definitely got a good enough understanding to be able to be successful at GCSE. Okay, thank you very much. Goodbye.